One of the toughest things to do in setting up a water damage project is balancing the rate of evaporation and the rate of dehumidification. You just cannot allow the rate of evaporation to be higher than the rate of dehumidification because humidity will build up and create all kinds of damage and stop the drying in the process. The problem is we just don't know exactly how quickly water is going to evaporate. How much water is going to be turned from liquid into vapor and be pushed into the air, pushing the humidity level up? It's anybody's guess. There are so many variables that we can't accurately account for things such as the permeability of the materials that are wet, the amount of saturation in those materials, the temperature swings the building is going to experience during the drying process, the amount of humidity that is going to infiltrate into the building from the outside, or if it's dry outside, how much moisture is going to exfiltrate from the building to the exterior. There are not a lot of absolutes in water restoration, and this is one of those things. We need something to help us at least make an educated guess to get us started. Class of water is that thing. Essentially, class of water looks at the type and amount of materials in a building that are wet. We can accurately account for that. Then, based on that, we can make an educated guess as to the rate that moisture is going to evaporate into the air. From there, we can make an educated guess as to the starting point for how much dehumidification we might need. I told you this is an art based on science. Okay, so far we've talked about what water restoration is and why it's so important that we start services as soon as possible to limit structural damage and microbial growth. We also looked at some of the tools and equipment that are necessary to complete our job, such as air movers that increase the rate of evaporation and dehumidifiers that remove vapor from the air. Working safely was our next subject. And it should be the first priority on our projects, and that needs to start with the inspection process. The microbiology of water helped us see that when buildings are contaminated, we clean first, then we dry. On contaminated losses, containment, PPE, and air filtration devices serve important roles in protecting workers and occupants. Then last, we looked at meters and explained the value of moisture sensors and IR cameras and moisture meters and finding the perimeter of water, establishing how much moisture is held in the materials, and whether or not we're set up to dry. Now we're going to talk about class of loss. Class of loss refers to the amount of evaporation that we anticipate coming from those wet materials. And a class of loss is determined by looking at the amount and type of materials that are wet. Now, it's very important that we figure out how much evaporation we think is going to occur. We've got to at least guess at it, because as evaporation occurs, or we're turning the water that's on or in those materials into vapor, what do you think that's doing to the humidity of the room?
It would definitely make the air more humid, and that would make it harder to dry.
It would also damage the contents and the structure if the air gets too wet.
You guys actually nailed both of the points, and I'm going to take credit for that. The fact that you already knew that means that I'm an awesome teacher. Yeah, seriously, though, they're exactly right. So here's a principle that always proves true. To create conditions for drying, heat the materials and dry the air. Now, you're going to hear me say that a lot of times through the course of this class. But when the rate of evaporation, or putting moisture into the air, we're getting it from the materials into the air, is higher than the rate of dehumidification, which dehumidification is removing that moisture from the air with dehumidifiers, the rate of drying is going to slow down, right? And that's bad. It's also bad when the relative humidity of the environment exceeds 70%. So it's gotten too high. It exceeds 70% relative humidity. At that point, the potential for secondary damage or microbial damage goes way up. And you're definitely in a situation where the conditions are ideal for secondary damage. Now, what's secondary damage? Secondary damage is damage to hygroscopic building materials or contents because of high humidity. In other words, the water didn't actually touch those materials, but the humidity does and creates what we call secondary damage. Now, let me walk you through a demo from our lab, and you're going to see a demonstration of how this happens, and then you can better understand the need for dehumidification to be greater than the rate of evaporation. What I'm going to show you is how high humidity affects the weight of a material. Now, why does that matter? Well, the benefit of seeing that is it helps you understand that water doesn't actually have to touch materials for the material to become wet. And damage can occur because materials are wet just due to high humidity. Now, that will help us to see that it's very, very important to manage humidity throughout the drying project. So to see this, let's first weigh these common materials dry, and then we're going to put them into high humidity and see what happens. Now we've written down the weight of those materials, and we're going to put those building materials into this container, and we're going to increase the humidity dramatically. We're going to leave these materials in this high humidity just for a short period of time, just a few minutes, and then we're going to pull them out and see if the weight has changed at all. Because any change in weight is a change in moisture content. All right, so now we've allowed these materials to sit for a few minutes. We're going to pull them out and see if there's been any change in the weight. And remember, any change in weight is a change in moisture content. Now, as you can see, each of these materials has increased in weight since they've been exposed to this high humidity. And that means that all of them have increased in moisture content. Because basically, moisture content is describing the amount of the weight of the material that's water compared to the weight of just the material itself. In other words, if a material weighs 10 ounces when it's completely dry, and then we start adding moisture, then we reweigh the material and it weighs 12 ounces, we've added 2 ounces of water weight to the material. Now, to figure out moisture content, we can divide the water weight by the original weight to come up with moisture content. That's what a moisture content percentage is. In this example, the water weight is 2 ounces. That's what we said we've added to this material, divided by the original dry weight of 10 ounces. When we divide those two, it gives us a 20% moisture content. Water doesn't have to touch materials to get them wet. That can happen when there is just high humidity in the building. So we need to get humidity control started right away and then keep the relative humidity low throughout the drying process. So that's why we have to figure out class of loss, or what we anticipate the rate of evaporation being during the drying process. Now, we're going to take these materials and put them back into that container, and we're going to continue to look in on them and see what happens. What you're going to see is what secondary damage looks like. Now, we've been watching these materials for some weeks, and you can see the effect that relative humidity has had on these materials. In a pretty short period of time, this high humidity has caused visible microbial growth. And this is another reason why we manage humidity throughout the drying process. And we start that as soon as we arrive on the job site. In order to know how much dehumidification we need, we've got to understand class of loss. And class of loss is there to help us anticipate the rate of evaporation. Now, remember, when humidity levels are high, drying is going to be slow. And when relative humidity is in excess of 70%, we can have structural damage. And as you can see, microbial growth can occur. So now it's very clear that we do have to manage humidity levels in a safe range. And in order to do that, we have to have sufficient dehumidification. Obviously, we need more dehumidification in a water damage environment than we would in a building that wasn't wet. So how do we figure out how much dehumidification to use? Well, in order to initially, now I use that word initially, but initially determine how much more dehumidification we would need than normal, we need to anticipate the rate of evaporation. How do we do that? Well, this rate of evaporation is classified into 4 classes of loss in the S500. So to get more information on this, we're going to go to our S500 expert, Judge Nicholas III, Esquire. Judge, what can you tell us about classes of loss?
First, we have Class 1. This is the least amount of water absorption and evaporation load. Water intrusion where wet, porous materials, for example, carpet, gypsum board, fiberfill insulation, concrete masonry, textiles, things of that nature, represents less than 5% of the combined floor, wall, and ceiling surface area of the space, and where materials described as low evaporation materials, such as plaster, wood, concrete, masonry, or low evaporation assemblies like multi-layer wallboard, multi-layer subfloors, gym floors, things of that nature, have absorbed minimal moisture. Secondly, you have Class 2 water. This is Class 2 is a significant amount of water absorption and evaporation load. That means you have water intrusion where wet porous materials such as carpet, gypsum board, fiberfill insulation, concrete masonry unit, things of that nature, are between 5% and 40% of the combined floor, wall, and ceiling surface area in the space, and where materials described as low evaporation materials such as plaster, wood, concrete, masonry, things of that nature, or low evaporation assemblies, multi-layer wallboard, multi-layer subfloors, gym floors, things of that nature, have absorbed minimal moisture. Next you have Class 3. This is the greatest amount of water absorption and evaporation load, where you have water intrusion where wet, porous materials such as carpet, gypsum board, fiberfill insulation, concrete, masonry unit, they represent more than 40% of the combined floor, wall, and ceiling surface area in the space, and where materials described as low evaporation materials such as plaster, wood, concrete, masonry, or low evaporation materials, once again, multi-layer wallboard, multi-layer subfloors, gym floors, other complex assemblies, have absorbed minimal moisture. Next you have Class 4. This is deeply held or bound water. Water intrusion that involves a significant amount of water absorption into low evaporation materials, plaster, wood, concrete, masonry, or low evaporation assemblies, multi-layer wallboard, multi-layer subfloors, gym floors, complex and built-up assemblies. Drying may require special methods, longer drying times, or substantial water vapor pressure differentials. Now, I read some highly important definitions there that are established principles. You should make note of them. Write them down in your book. Now, since Class 1 has the least amount of wet surfaces, less than 5% of the surfaces in the affected areas, if you recall, it will have the least evaporation, resulting in a correspondingly lower amount of required dehumidification. Now, Class 2 is a significant, and some would say large, amount of water absorption and wet porous materials. Approximately between 5 and 40% of the surfaces in the affected areas are wet. So naturally, this means that a greater amount of evaporation will occur, and naturally more dehumidification will be necessary. But the Class 3, it says the greatest amount of water and evaporation load with more than 40% of the surfaces in the affected areas wet. As expected, it would also have the greatest rate of evaporation and need more dehumidification. Finally, you have Class 4. This one is a bit different, sometimes called specialty drying situations. Now, in this class, the problem is not so much how much evaporation will occur, because the rate of evaporation is low. Rather, it's the fact that the bound water in these low evaporation assemblies or materials will be very difficult to remove. Therefore, drier as necessary, and that means more dehumidification would be required. It is all quite simplistic in concept. However, a true professional must know the difference in the definitions of class of loss if he is truly going to be accurate. That is all.
Thank you, Judge. Or should I say, Your Honor?
This is a water damage course, not a court of law. You can call me whatever you like within reason, except, as you Americans say, don't call me late for dinner. But while we're on the subject, it's Judge. Or it's Your Honor.
You're the best, Your Honor. So now that we've discussed class of loss and definitions, I recommend you study these. And the reason why is because when we get into dehumidification, we're going to refer back to class of loss. And if you don't know the class of loss on a specific water loss, you can't figure out initially what your dehumidification needs are. And that's going to be a problem.
Definitely need to put a little time on this so I can remember these.
Yeah, that would be a good idea. Now, they're not difficult. It's just memorization, but that requires a bit of time and review. So do the quizzes at the end of this module, and then you're going to be ready to move on.